In this video, we're going to look at the chapter of the gaseous state in the A-level syllabus. There are essentially two parts to this chapter. The first part, we're going to learn an equation called the ideal gas equation, and we're going to make use of this equation as well as the different variations of this equation to solve calculations involving gases. We are also going to look at how we can make use of the equation to derive graphical plots of a gas under different conditions. The second part of this chapter, we're going to look at what it means for a gas to be called an ideal gas, the assumptions of an ideal gas, and under what conditions would a gas behave ideally, and under what conditions would a gas not behave ideally. I know certain words sound very unfamiliar at this point in time, but don't worry, we're going to look at it in the next, in this video as well as the next few videos. Now in this chapter, we are focusing on gases, so let us first do a recap of what we already know or what we have already learned about gases. In O-levels under kinetic particle theory, we learned that particles are in continuous random motion. When we zoom into a gas, we find that the particles are far apart, very disorderly, they move at high speeds in all or random directions. Okay, and because of that, the forces of attraction between the particles are actually very, very low. We also learn in chemical calculations that 1 mole of any gas, so regardless of which gas you are looking at, the molar volume is 24 dm cube under room temperature pressure conditions. Okay, and then we went on to look at Avogadro's relation, where we are when we look at reacting gases, the volume ratio is actually equal to the molar ratio. So if we have 1 mole of nitrogen reacting with 3 moles of hydrogen, it means that 10 centimeter cube of nitrogen will react with 30 centimeter cube of hydrogen. So for those of you who are pondering the basis of Avogadro's relation, why is it that volume ratio for gases is equal to molar ratio? It all boils down to the fact that 1 mole of any gas, they have the same volume. And for those of you who ponder even deeper as to why 1 mole of any gas would occupy the same volume, because if you think about it, the particles actually have different sizes, so they ought to occupy different volumes by right, okay? But that has something to do with the arrangement and movement of particles as we have seen in kinetic particle theory. So even though different gases may have different particle sizes, all right, but because they are very, very far apart under room temperature, they occupy a vast volume of the container. So if you consider the volume of the particle, right, compared to the volume of the container, you will find that the difference in the size or volume of the particles are actually quite insignificant. Okay, so under room temperature conditions, regardless of the size of the particles, 1 mole of any gas would actually occupy roughly the same volume, which is 24 dm cube. At this point, I want to quickly point out the slight differences between what we have learned earlier and what is in the A-level syllabus. Now, we have learned in O-levels that 1 mole of any gas occupies a volume of 24 dm cube at RTP. What does RTP stands for? It stands for room temperature and pressure. So back then, we used to define room temperature as 25 degrees Celsius. However, in the A-level syllabus, in accordance to international changes as well, room temperature is defined as 20 degrees Celsius. Okay. On top of that, in the A-level syllabus, we also learn the molar volume of a gas under a different set of conditions known as STP. Now, what is STP? STP stands for standard temperature and pressure. So standard temperature pressure essentially means a pressure of 1 bar. Okay, bar is another unit for pressure. So pressure is usually defined as pascals, okay, atmosphere, or bar, or even something called mmHg. Right, these are the different variants of the units for pressure. So it will be good if you know how to convert from one to the other. 1 bar is actually equals to 10 to the power of 5 pascals. Okay, and 1 atmosphere is 101325 pascals. Okay, and then for mmHg, 760 mmHg is equivalent to 1 atmosphere. Okay, so STP represents a pressure of 1 bar, which is 10 to the power of 5 pascals. Essentially, 1 bar and 1 atmosphere is very, very close, okay, because it's just a difference of 1325 pascals. All right, and the temperature at STP would be at 0 degrees Celsius, which is 273 kelvins. So in the A-level syllabus, you need to know not just 1 molar volume. You need to know that at RTP, okay, the molar volume is 24 dm cube. At STP, the molar volume is 22.7 dm cube. Now, before we even go on to look at the ideal gas equation, I just want to point out from this slide that whenever we look at a gas, we usually describe it using 3 variables. Okay, we can see that volume is one of them, so we always talk about volume of a gas. Okay, and of course we look at temperature, because temperature will actually affect the other variables as well. And then the last variable that we look at is pressure. Okay, so whenever we look at a gas, or whenever we describe a gas, we describe it based on 3 variables: volume, temperature, and pressure. Okay, and then so what scientists long time ago discovered is this, that the pressure, volume, and temperature of a certain amount or number of moles of gas is actually related by an equation, and they call this equation the ideal gas equation. Now let us look at the variables in the ideal gas equation. I guess we are familiar with P. P represents pressure, V represents volume, T represents temperature. Okay, and earlier I mentioned for certain amount or number of moles of gas, so N represents the number of moles of the gas. The new variable that we are looking at here is R. R is actually a constant. Okay, so it has the same value for any gas. Okay, we call this the ideal gas constant. Okay, and the value of the ideal gas constant is 8.31. Okay, and it actually has a unit, which is joules per kelvins per mole. Okay, and since 8.31 is specific to these units over here, so when you make use of the ideal gas equation, okay, when you substitute values into PV equals to nRT, okay, it's very, very important that your values must be substituted in standard units. Okay, so what do I mean by that? So whatever pressure that you substitute in must be in pascals. It cannot be in bar, it cannot be in atmospheres. Whatever volume that you substitute in must be in meter cube. This is the most important variable, because very often in questions you are given volumes in terms of centimeter cube or decimeter cube. Okay, remember to convert the volume to meter cube. Okay, temperature must be in kelvins. Okay, very often in questions you'll be given temperature in degrees Celsius as well. All right, only when we substitute P, V, and T in terms of the standard units, then can we use the ideal gas constant of 8.31. So in this very first example, we're going to look at how we can use the ideal gas equation to determine one of the unknown variable. In this case, we are looking at phosphorus vapor, which is a gas. So we are given the pressure, we are given the temperature, okay, and we are asked to find the volume or the molar volume. All right, given that we are looking at molar volume, so essentially we are given the number of moles to be 1. Okay, so again the ideal gas equation looks like this: PV equals to nRT. We are given volume, we are given pressure, we are given temperature, and we are given number of moles. So again, whenever you use the ideal gas equation, bear in mind that you need to convert all your variables into their standard units. So pressure would be 31.89 times 10 to the power of 3. This is in pascals. Volume is what we need to find in meter cube. N equals to 1. R is 8.31. And temperature is given to be 550 degrees Celsius. So we need to convert it into kelvins. So to convert temperature from degrees Celsius to kelvins, we need to add 273. So in this case, we will arrive at a volume of 0.214 meter cube. Okay, you can leave it as meter cube or you can convert it to 214 decimeter cube. So to convert meter cube to decimeter cube, essentially we multiply it by 1000. dm cube to cm cube is to multiply by another 1000. So when, for example, if you are given a gas with a volume of x centimeter cube, remember to convert it to meter cube first, which in this case we have 6 zeros before you make use of the ideal gas equation. Now, other than being able to substitute values in terms of standard units into the ideal gas equation, we also need to recognize the different forms of the ideal gas equation. So right now I'm going to show you that the ideal gas equation can actually be transformed into different forms. And the starting point is actually this N. We have learned in chemical calculations or mole concept that number of moles is equals to mass over molar mass, okay, or relative molecular mass. So essentially, we can change the ideal gas equation into this. So we can actually make use of the ideal gas equation to find the mass of a gas given the other variables, or even the molar mass of a gas given the other variables. Okay, we can make one more transformation, which is this. We can rearrange the equation such that we have this. We can bring volume over, so we have mass over volume and RT over molar mass. And why is this significant is because mass over volume, we are essentially looking at density. So pressure of a gas is actually related to the density times R times T divided by the relative molecular mass or the molar mass. Okay, so as mentioned, it's important for you to know these two other variants of the ideal gas equation. So in this question, it's very similar to the one before. We are looking at phosphorus gas or phosphorus vapor. We are given the pressure, we are given the temperature. In this case, we are given the density as well, and we are required to find molecular mass. So if you are thinking about the ideal gas equation, PV equals to nRT, you may be stuck because there's no density, there's no relative molecular mass in the equation. Okay, however, if you can recall that there is a certain variant of the ideal gas equation which has these variables, then we can easily solve this by using that equation. Okay, so the variant, you can either memorize it or you can derive it on the spot. It's not very difficult. So pressure equals to density times R times T divided by relative molecular mass. Okay, the next thing is to recall that we need to substitute the values in terms of the standard units. Now, students generally will be able to recognize, will be able to convert your pressure to Pascal, your temperature to kelvins, okay, but some of them may miss out this, that the density is given in grams per dm cube. Okay, so remember the standard units for volume is meter cube, so you need to first convert this to grams per meter cube. Okay, and how do you do that? To convert meter cube to dm cube is actually to multiply by 1000. Okay, so in this case, our density should be 0.579 times 10 to the power of 3, okay, times 8.31 times the temperature in terms of kelvins, okay, divided by the relative molecular mass. That will give us a pressure of 314 0.89 times 10 to the power of 3. Okay, so that will allow us to find the relative molecular mass to be 124. Okay, bear in mind that we are looking for the relative molecular mass. So relative masses have no units, they are dimensionless. So please don't make the mistake of writing grams per mole in your answer. Next, we need to find the molecular formula of phosphorus vapor. So since phosphorus gas has a molar mass or relative molecular mass of 124, we need to recognize that relative molecular mass is obtained by summing the atomic masses of all the atoms in the molecule. Okay, summing up all the atomic masses. So we need to look at phosphorus now. Phosphorus has an atomic mass of 31. All right, so what that means is that in one molecule of phosphorus, it is actually made up of 4 phosphorus atoms. Okay, that would also mean that the formula of phosphorus vapor is P4. Now in this part, we're going to look at how we can use the ideal gas equation in questions related to a change in state of the gas. Now the term change in state may be a bit confusing. Over here, change in state doesn't mean that we are changing from solid to liquid or liquid to gas. All right, when we are looking at gases, when we say change in state of a gas, it means that we are changing either the pressure, the volume, or the temperature of a gas. Okay, so for example, a gas may be at a particular state of P1, V1, and T1. Okay, it may be changed into another state where the pressure changes, the volume changes, and the temperature changes. So when we say that there's a change in state of a gas, it means that either the pressure, volume, temperature, or all three of them are changed. Okay, so starting from the ideal gas equation, now imagine that a gas is in this initial state where we have P1, V1, T1, as well as maybe N1. All right, then we can construct this equation we can substitute the values into the ideal gas equation, and then it changes to a different state of P2, V2, T2, and N2. All right, so we can substitute it into the ideal gas equation as well. Now, when we look at these two equations, equation 1 and equation 2, the common thing about these two equations is that R is the same. Okay, so if we make R the subject, we can find that the two states of the gas are actually related by this equation. Okay, this is a very, very, very powerful equation, okay, that we can make use of for questions involving a change of state in the gases. In fact, this equation is so powerful that we can make use of it to derive all the other gas laws that we're going to learn in this chapter, as well as the equations associated with these gas laws. Now, these gas laws are what I affectionately call them as ABCD laws. A stands for Avogadro, Boyce, Charles, and Dalton's law. Okay, so what each of this law is that we are looking at the change in state of a gas under certain conditions which remain constant. Now, the first law that we're going to look at is Avogadro's law. Avogadro's law, we are looking at the change in state of a gas when the temperature and pressure remains constant. Okay, so what happens when the temperature and pressure remains constant, or how can we make use of the equation that we saw earlier to derive the law, is this. When a variable remains constant, we can actually eliminate it from the equation. So for Avogadro's law, temperature and pressure remains constant, so I'm going to eliminate pressure from the equation and then temperature from the equation. So what we see from the remaining equation is this, that the volume of a gas is actually directly proportional to the number of moles. Okay, so that also leads us to our Avogadro's relation, where the volume ratio is equivalent to the molar ratio. Now this variant of the equation may not be clear enough, so I'm just going to rearrange it into this. Okay, so from here I hope you can see clearly that the volume of gas is directly proportional to the amount, and the volume ratio is actually equals to the molar ratio. Now we'll look at Boyle's law. For Boyle's law, what is constant is the mass or the number of moles of the gas is constant. So once again, I can eliminate it from the equation. Next, the temperature is also constant, so let me erase the temperature. So the remaining equation looks like this: P1 V1 equals to P2 V2. All right, let me just very quickly rearrange it to give me V1 over V2 equals to P2 over P1. So from this equation, we can see that the volume of gas is actually inversely proportional to its pressure. So that's Boyle's law. For Charles' law, we are looking at conditions of constant pressure and also fixed mass. So we can erase pressure and we can erase the number of moles because they are constant. So what is remaining is this: V1 over T1 equals to V2 over T2, or once again, let me just rearrange it to give me V1 over V2 equals to T1 over T2. So what it means is that the volume of gas is actually directly proportional to its absolute temperature. Okay, once again, temperature, we are looking at standard units of kelvins, so that is why we need to emphasize that it's proportional to the absolute temperature. Now we have looked at situations where the temperature remains constant. This is known as Boyle's law. All right, we have looked at the situation where pressure remains constant. This is Charles' law. There's also another situation where the volume of a gas remains constant. Now the approach is the same. When the volume of a gas, of a fixed mass of gas remains constant, we can eliminate the variable of volume and number of moles from the equation, and what we get is this: P1 over P2 equals to T1 over T2. So what it means is that pressure of a gas under constant volume conditions is actually directly proportional to its absolute temperature. Okay. Now some students will actually memorize, Boyle's law, Charles' law, and so on. For me, I think that is not required. All you need to do is to remember what are the variables that remains constant. Okay, in fact, when you're solving calculation questions, they are not required to state which law is it, all right, but you just need to recognize which variables remain constant and therefore derive the equation that you should use. So let us look at an example now. So we are looking at argon gas. We are given the temperature of 18 degrees Celsius and a volume of 2.67 centimeter cube. All right. Then the temperature is lowered to 0 degrees Celsius. So that indicates a change in state of the gas. Okay, change in state. Okay, and once there's a change in state, remember we need to make use of this equation: P1 V1 over N1 T1 equals to P2 V2 over N2 T2. Okay, so we are required to find the new volume. Now the question tells you that pressure remains constant. Okay, so once again, there's no need for you to identify what law are we looking at. If pressure remains constant, let us remove pressure from the equation. Okay, and when the temperature is lowered, we don't expect the amount of gas to change. So the equation that we should be using is this: V1 over T1 equals to V2 over T2. Okay, now when using the change in state equations, okay, when using the equations associated with Charles' law, Boyle's law, sometimes the units of your pressure, the units of your volume, they are not important. Okay, why do I say that? Let me first rearrange it to this. So we want the new volume. So we have this. Now earlier I mentioned that the units of the pressure and volumes are not important. Reason being, when you convert from one unit to the other, essentially we multiply or we divide by a constant. So for example, volumes, all right, let's say V2 over V1, all right, if something is in centimeter cube, all right, and you convert it to meter cube, you need to divide by 10 to the power of 6. Okay, and then in the denominator you need to divide by 10 to the power of 6 as well. All right, so when you take V2 over V1, essentially even if you convert it to meter cube, all right, the constant will be cancelled out. So again, when you are using change in state equations, the units of volume and pressures are not important. Okay, even if you don't convert them into the standard units, you will still arrive at the correct answer in whatever units that you have chosen. However, the units for temperature, you need to remember to convert it to kelvins. Why? Because when you convert degrees Celsius to kelvins, we are not multiplying it by a constant, but we are adding a constant. So when you take T2 over T1, the constant, they do not cancel out. Okay, so when you're using temperature over temperature, do not just leave it in degrees Celsius. It doesn't work that way. You need to convert it into kelvins. However, when you're taking volume over volume or pressure over pressure, the units doesn't matter because the constants will cancel out. So in this case, we can just very quickly find out the new volume, which is this, equals to T2, which is your 0 degrees Celsius, over 273 plus 18. Give us a volume, a final volume V2 of 2.5 centimeter cube. Okay, notice again that the volume that we find is in terms of centimeter cube. Reason being, the volume that we substituted in was in centimeter cube. So the last of your ABCD laws would be Dalton's law of partial pressure. So what it states is that in a mixture of gases that do not react, so the key thing is that they do not react with one another, all right, the total pressure of the mixture or exerted by the mixture is actually equals to the sum of the partial pressures of the constituent gases or the gases in the mixture. So there is an unfamiliar word here, which is partial pressure. What does partial pressure mean? Okay, so let me just explain the law in terms of an example. So let's say I have a mixture of hydrogen plus nitrogen plus argon. Okay, hydrogen exerts a pressure of P1. So if hydrogen were to be alone in the container, it would exert a pressure of P1 or pH2. Okay, if nitrogen were to be alone in the container, it will exert a pressure of Pn2, and argon a pressure of PAR. Okay, so the total pressure in the container is actually equals to the sum of the pressure exerted by hydrogen plus the pressure exerted by nitrogen plus the pressure exerted by argon. Okay, so once again, what is partial pressure? Partial pressure of a gas in a mixture is the pressure exerted by that gas if it were to be alone in the container. Okay, so a general equation for the Dalton's law is P total equals to PA, B, and so on. So A and B represents the gases in the mixture. Okay, a more important equation for Dalton's law of partial pressure is this, that the partial pressure of a gas in the mixture is actually equals to the mole fraction. Okay, this is called mole fraction. Okay, it's given a symbol of chi. All right, so the mole fraction represents the number of moles of the gas in the mixture over the total number of moles. This is known as mole fraction. So partial pressure of a gas is equals to the mole ratio or mole fraction times the total pressure. Okay, in fact, we can derive the bottom equation from the top. It all starts with the ideal gas equation. So let me very quickly show you how. So let's say we are looking at the partial pressure of gas A. So using the ideal gas equation, it will be equals to NA RT over V, okay, and then the total pressure is actually equals to N total RT over V. Okay, so over here, if we take equation 1 divided by equation 2, we'll arrive at this PA over P total equals to NA over N total. All right, and then if we just bring your P total over, we arrive at the equation. Let us look at an example now. So in this example, we have a flask of helium with a volume of 2 dm cube and 0.6 atmosphere is connected to another container of oxygen which has a volume of 1 dm cube and pressure of 0.9 atmosphere. Okay, they are connected, and then when you connect, the key thing is this: now helium can diffuse over to the flask containing oxygen, and oxygen can diffuse over to the flask containing helium. All right, so what it means is that now both gases can occupy a new volume of 3 dm cube. Okay, so volume changes. So this tells you that there's a change in state. So therefore, since your temperature is constant, all right, since your temperature is constant, and of course number of moles wouldn't change, then your pressure, the new pressure of helium will change. Okay, or rather the pressure of helium will change, the pressure of hydrogen which will change. So we need to find what is the new pressure of helium and what's the new pressure of hydrogen. That is quite simple. So you just need to make use of the change in state equations. Quickly find out that the new pressure of helium is 2 over 3 times 0.6, and then the new pressure of hydrogen is 1 over 3 times 0.9. Okay, next they want you to find the final pressure, which is the total pressure in the connected flask. So this is where we need to use the law of Dalton's law of partial pressure. Since helium and oxygen do not react, the total pressure is just the sum of the partial pressures. Okay, and that will give us a final pressure of 0.7 atmospheres. So in this video, we have been introduced to the ideal gas equation. Once more, when you substitute values into the ideal gas equations, they must be represented in the standard units. Next, we saw that the ideal gas equation can be manipulated or can be converted into different variants containing molar mass or relative molecular mass and even density. Okay, in the second part of the video, we look at change in state of gases. When there's a change in state, we can make use of the very powerful equation P1V1 over N1T1 equals to P2V2 over N2T2 to derive the final equation depending on which variables remain constant. Find out the new value of a particular variable after the change in state.